Hello, welcome everyone. Welcome everyone at T3 at this late night after this hot day in the cold now. With us is forensic scientist Ruud Schramp from the Dutch Forensic Institute. It's a government institute, but he'll probably explain everything about it. And he does awesome things with running servers, and they also do things with BGA chip. He will have a video at the end, but if you want a real-life demonstration of the techniques he shows you, you have to go to, what was it called again?
Garrison, is our village.
Okay,
it's at the end.
Please welcome Ruud Schramp. At the end there will be time for Q&A, by the way.
Okay, well, welcome you all. We are a decently big group. Well, my name is Ruud Schramp. I work for the Netherlands Forensic Institute, which is a government organization. My presentation is about acquiring RAM, because we find a lot of interesting things in RAM nowadays. The agenda of the meeting is pretty simple. I'll give a very short introduction about NFI, because we all like techniques and we don't want to have too much mumbo jumbo. Some background on the case, the problems I ran into and solutions I found, and then into the final implementation phase, which ends with a lot of noise, which is the demo. Or at least in this time, a video here, because it's a very long demo. It takes almost an hour if you don't want to see everything. But in the video we can compress that a bit to 2 minutes or 5, something like that. So the NFI is a government organization. We are not the police. We are actually a neutral party, mostly working for the judges. We, well, as you can read, try to be as transparent as possible. So this presentation is a very big shooting in my own foot. It's giving away a method that, of course, you should never have learned about, and hopefully you will never implement any features that will try to circumvent it. So do not listen at all, don't pay attention, because it will make my day a lot harder. So this is the case. In a criminal investigation, the police found some servers in a big rack at a server room, and they're all the same. If somebody notices his own server, they can raise their hand. So why do we bother around RAM? Well, perhaps a lot of IT personnel here are handling all kinds of virus incidents, and they will look into the task list and see which programs are running, if there are any fancy programs you don't expect, things being hooked, or strange TCP sessions going to the CNC somewhere, everywhere, which is of course very interesting if you're in the IT department and you can find some viruses on the left or the right. So that's typical one case of memory analysis. But forensically speaking, I don't care about those kind of things, at least not that much. I'm only looking for one thing, and that's a password, a key, or anything that will actually decipher the TrueCrypt encrypted disks you're all making nowadays. I think in the other tents a few blocks away, they're now installing TrueCrypt on a, let's say, a regular basis, and so do the criminals. So that's a big pain for anyone doing a criminal investigation. Sometimes you also want to do other stuff, but that's not that important. So how do you get to the RAM? Well, first you have to have a machine which contains RAM. Well, every machine contains RAM. That's not a problem, but normally when it's turned off, it's kind of a dull RAM, because it's an empty RAM. So you want to have your RAM filled with relevant information. And I think it was the joke what Ahmed said, it's location, 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 and here it's timing. You want to make sure the machine is running, and then you knock on someone's door when he's grabbing his coffee, and maybe he has locked or he hasn't locked his PC, but at least it's on. If you're lucky, it's open, and then there are all kinds of nice tools, forensic tools, like from Guidance, HBCare, Maniac, WinDD, which when you click some things, you actually write the memory to a stick or an external disk, and then everything is happy and we're gone. But there's a big if. It only works if you can actually click something. So what do you do when you just have got this nice login prompt? Or, well, on Linux just a very black screen. Well, then there are some methods, and the most well-known and well-described one is using Firewire. Please raise your hand who has got Firewire on his new laptop. So those are... then my attack would still work. But then, of course, so that's a big of a problem. A lot of PCs don't have, I saw a few hands, but a lot of people were not raising their hands, and a lot of modern PCs don't have Firewire anymore. Alternatives, you can try to put in some cards. There has been some papers, old papers, like the triple card, Copilot. There has been a forensic RAM expression device. All devices I've read about in papers where I haven't actually physically seen, because you can't buy them. And even when you can buy them, even the papers say, well, if you want to try to hot plug them, it's kind of dodgy. So the other alternatives, well, we don't care about doing it in the host OS, we reboot the system. So you turn it off, we do it very fast, because you can just press Ctrl-Alt-Delete, or you hit the reset pin, something like that. And then it will reboot, and then you can run a very tiny operating system, or even not an operating system, even smaller, like MS Random, which runs from a small partition, and then you have a very small impact on your RAM, and the rest can be dumped straight away. So that's been done quite often. But you can be out of luck. So what is the out of luck here? We've got a PC which hasn't any Firewire. When you log in, there actually is not any prompt at all, because why would you need to log in on the server? And when you reboot it, it will immediately wipe your memory. And why does it do that? A server PC typically got ECC memory, which has got parity bits. And as far as I know, if you've got this machine is completely shut down, let's say off for a few days, and you turn it on, all those memory bits will flip into random positions, or not that structurized, and that means that the parity bits will actually not match the content. So when you would read that kind of memory, you would actually get parity errors all the time. So the BIOS, before you can actually boot your OS, make sure the parity bits are all correct. And it does that in a very simple way. It writes it full with zeros, the full memory is wiped. And that's too bad if you want to look for keys in the memory. So this is my cradle. I should actually go on my knees now. And okay, I believe removing DIMMs will typically kill everything in that. And there are some stuff about cooling them, because there are papers about cold boot attacks, and I think it was about cooling them down to minus 40, 50. But I haven't actually seen that working that much. The papers I've read are really old already. If you think about, well, they're perhaps halfway 2005. So in internet years, we are some rounds of more ahead of that. If you want to try something in a hot plug bug, like a standard PCI bus, that will give glitches, and your OS doesn't like that one. And if you're talking about the DIMM, which is also, of course, an electronic interface, it runs at something like, I think, 666 megahertz. So now we're sticking along wires to measure there. It can probably be done with a very fancy equipment. Then you turn it off first, insert it, make sure you've got various. So hopefully somebody will just come to me now and say, no, you're totally wrong, you don't, just this is the way to solve it. So in this case I got this stack of PCs. They were brought to me on a trolley. This stack with a lot of UPSs around it. And please get me the memory, because there were some signals that may be important. So then you start looking at the motherboard, and you find all kind of connectors. I've got connectors here, there's some strange looking thing called BIOS, but also a connector here. We've got the PCI Express bus. I've got this very nice DIMM slots, and of course a lot of test and measuring pins all over the board. So then you start talking to HP, so could you please explain to me what all these undocumented ports do? And they say, well, that will be tricky. So I sent a few more mails, and in the end, after about 2 months of calling and nagging, I ended up in Bangalore, and they were very grateful because they sent me just a very simple pinout just of these 2 ports, and the rest was proprietary, hard to get. So So what did I find? I found something which was labeled debug port. And if I'm a forensic scientist and I find the debug port, I'm almost cheering already. Debug port, that sounds great. There's a TPM port, which actually is a low pin count interface port. But without an interrupt, because the TPM doesn't give interrupts. And without a bus master pin, because the TPM does not need to do DMA or anything of that kind of memory transfers. Of course, you've got PCI Express, and then some other stuff like serial peripheral interface, bus, SATA, USB, I2C, and serial. But those are typically buses that don't give you any memory access, perhaps indirectly. So this debug port, that was so sad. It was labeled debug port, but actually it's just LPC. So the Intel chip has got a debug port. If you would ever find it on a motherboard, then I would be cheering again, because it can do very neat stuff, although you need to buy the specifications first. So the LPC bus is a nice one, because theoretically it would allow you to become bus master. LPC is the replacement of ISA. I think it's only about 8 wires, 9 wires, something like that. But the bus master pin is never needed for normal use, so they're actually almost never on the a pin on the circuit board that will give you access to it. So what I tried is, well, we know of course which pin on the back side is it, and I just try to find it and just measuring, and okay. So that took some time. Didn't work. So I started focusing at the BIOS, because you can also boot from other interfaces, not from a standard BIOS, but from PCI Express, for example. So that would be an option, to put an alternate interface on the PCI Express. But then you need to access what they call function straps. So these are very small resistors that push the Southbridge and Northbridge in a certain configuration at power on. So it does need to know at least something. Okay, I'm going to boot from the LPC bus, or from the I2C memory chip, or from PCI Express. Such kind of things you can choose by adding or removing resistors. So I tried to find those one. That's a pain, and eventually I didn't find them. So, well, can I just insert a card? For example, can I insert a Firewire card? Because it's PCI Express. PCI Express is hot pluggable, at least so it's said. But the documentation of this chipset says, well, we do it about-ish. Never got it to work. But perhaps I should do one. Actually, I think I should investigate that better. But still you need to be able to do bus master. And there, the guy in the front row already pointed it out. Under software control, your host OS would actually allow you to become a bus master. So that's a PCI Express configuration register, which you need to set with a 1, and that's not done automatically. The host OS will need to put that bit on 1. So I was, what am I going to do? Panic. I've got still this stack, almost waiting now for 3 months, and I need to do something. Let's look at that BIOS. And the concept is very simple. We're going to do a standard reboot with like MS RAM dump, which I showed on the previous slide. But just make sure that this memory is not cleared. So I need something like a BIOS that does not clear my RAM. That sounds simple enough, right? But there are some hurdles to take. First of all, we need to get the chip on the main board connected physically without turning the main board off. And then you need something like, how am I going to get the data which is in the RAM out on something else? How am I going to use the disk, serial, USB? We need a way to turn it off and on very quickly, within milliseconds or microseconds preferably. Of course you need the BIOS, and then you need to initialize the main board, and I'll get to that. So how do you get a chip off? Well, that's the easy part, with a soldering iron. It's a nice one. It's got hot air flowing out. Don't put your hand against the shaft because you will burn. I've personally experienced, because I was a little bit shaky on my first experimentation. But that works fine. And then you can attach wires to the pods. So you've got these very thin wires, and you attach them to the main board, connect them to a programmer, and then you've got the development system. Of course, you start off with a reference PC and not on the thing you are investigating in the first place. I/O, well, keep it simple. So that's the beauty of most technical solutions, KISS. So we start off a serial, and later on, because there's this very nice LPC connector on the motherboard, and I found a very nice LPC power on self-test device. It's open source, you can download it. My first intention was to put the BIOS on LPC as well, because it's got flash chips and so on, but as I couldn't find the right resistor, that path was more or less blocked. The next step was we need a very clean and warm reboot, which is normally very simple. You just take the reset pins, connect them, and it's very fast. But there's no reset button on this motherboard. And if you press the power button for a few seconds, yes? Okay, good to know for the next time. Thanks. But I had another solution, so that's the good thing. But it's good to know. Actually, I used I2C. The Southbridge of this motherboard, the Intel Southbridge, actually has got an I2C command to do a reset. Which was lucky for me, otherwise I would have to find that solution, which probably would have taken me a few weeks more, I guess. And then we need our own BIOS. There are a lot of BIOSes around, most closed source, but there's one open source one, coreboot, and that seemed like a good starting point. But this motherboard, this particular motherboard, is not supported by coreboot. Perhaps at this moment it is, but at that moment it was not. But it's pretty fat for the purpose. So if you want to make a full BIOS, it will take a lot of time to actually do that, test that, make it production-wise correct. And you need, of course, to understand the motherboard to a very detailed level to do it correctly. And one of the problems is you want to initialize the RAM in the same way as a normal motherboard would have done. So you want to mimic the behavior of the original motherboard as well. But they've got something nifty, small, and they call it the serial in-circuit emulator. And that also is a kind of BIOS, but its only sole purpose is to make it possible to emulate your motherboard with QEMU. So it's a debugging tool for the coreboot project. So it's not an in-circuit emulator. It's very lightweight. It's about, well, I think 500, 800 lines of code. It's ROM only, and as I said, it's not a full BIOS. It's not intended to fully boot your BIOS. It's only intended to make a connection between your motherboard and QEMU on a different PC. So now I need to explain something about motherboards and how they work in general. Otherwise it will be very difficult to explain what happens. So typically you have a CPU on top, which is connected using a north bridge to the memory on the left side, and your video cards using the highest speed interface available for that kind of chipset. So typically you would connect your video card to the north bridge, south bridge typically called SATA, and you've got a separate Super I/O chip and BIOS on LPC. That's a traditional motherboard layout. My motherboard was a bit different, not that different, but a bit different. It's a server motherboard, and it's got what they call a baseboard management control, I think is the right word, which is more like you want to manage your system remotely, don't attach a video card terminal all the time, stuff like that. So it has the ability to have a display that can be sent over network cables, and all kind of keyboard can also be sent over IPMI. So it's more or less a stub that does the electrical part for the real devices, but at the same time also allows you to have a remote display and a remote keyboard and a remote serial and those kind of stuff. And in this case the memory is not on the LPC, but actually is a very small 8-pin chip on the SPI bus, which is apparently a novel technology, a method that Intel currently uses a lot. but when you reset it, it doesn't know about all those components. It's got some resistors, and the resistors tell it just the basic configuration. Typically only where to find the BIOS and not that much more. So that's a bit of a bummer, because for serialize to work I need something more, at least serial. So it would be nice if it would know about this whole chain with CPU, Northbridge, Southbridge, the BMC and the serial port. Well, this BMC is a bit of a bitch. Server Engines Pilot 2, not well documented at all how it works in detail, but it's a separate microcontroller, as far as I can judge, ARM based, for remote management. And it's got remote display, remote boot disk CD, remote on and off. You can actually share the serial port between the host and the BMC, so you can manage your system on a serial port and give it a reset using serial port as well. Should have used that one. And communications to the host OS, so you can send commands to the IPMI interface as well. And the default configuration at reboot is that the serial is the external serial port of the motherboard is connected to the BMC and not all the way to the CPU. So you cannot access it. And also at the ISA plug and play level, the ports are not configured. So you need to do some stuff before you can address the serial ports in the first place. So this is what you need to do. First you need to configure your Southbridge. You need to enable that as an LPC port. Some simple PCI Express registers are there. And then you need to explain it how to root port 2E, which is the ISA plug and play configuration port. I want to have some debug messages, so I want to root port 80. I want to root port 3F8, which is a serial port. And I need to reconfigure the BMC, otherwise my serial port will not be available. So you also need to be able to do the IPM KCS, which is a protocol to manipulate the IPM interface. So to configure the ISA device, you must figure out the correct device numbers. Well, that's simple. You just boot a reference system and then you can read them. Not that difficult. But you also need to find how to enable plug and play. And apparently there is some password you need to send to that port first before it will allow you to actually configure it. And that password is different for different types of Super I/O chips or those kind of stuff. So I had to reverse the BIOS a bit and find that constant. So I found the right device numbers, configure the ports, configure the BMC, then reset the BMC to the stable states, and then it's a ugly bit banger protocol that I could rip from the Linux driver somewhere, I think. Tell it to route serial to the host, and that's only 400 lines of C code. So actually it's pretty simple, but it takes some time to know how to do it and to figure it out and to reverse engineer the thing. So in the end I finally have a CPU that's running and can communicate over serial. No RAM still yet. So this is the way that serialize is intended to work. I've got two PCs, one I'm trying to initialize, that's the left hand side, and I've got a R&D PC or investigation PC which will run QEMU, and it's using Lua scripting as hardware abstraction rules, deciding okay, this port should be handled by the emulator, but other ports actually should be handled by the motherboard itself. So the serialized BIOS will handle very simple commands like, okay, read that byte, write that byte, read that word, write that word, do some I/O, read machine specific registers, write machine specific, all low level stuff that you would normally do straight to the motherboard is done here by the emulator, converted into command, sent all the way to the CPU, interpreted and then executed on the PCI Express configuration registers at North, Southbridge or whichever is relevant. And in that way we can let the standard stock BIOS do its normal thing. So do not have to implement a very big BIOS. The serialized BIOS is very simple, 400 lines of C code, and the stock BIOS running in the emulator will do the initialization for me. It's slow, but I didn't have to build it myself. So this is the small picture explaining that. And then you wait about half an hour. And after that half hour, if you're a bit lucky, it will initialize your RAM. And then serialize actually stops helping me, because it's intended by the coreboot project to debug a motherboard, which is what we just did, but it's not intended for forensics. And if you have to have one command of, let's say, 10 bytes to read 1 byte, and you want to copy 4G of memory, then you have a lot of overhead. So it was this time to stop it and see if we can actually do it a bit better. So I modified it for forensics, added functionality to make the dumping process efficient and as fast as possible, because it's a lot of memory. And so running from memory from the SPI BIOS, it's slow, painfully slow, and it's slow for several reasons. The main reason is that SPI-ROM is a serial protocol. So if you read one instruction, you actually have to clock out the address on the line, and then you will get some bytes back. The Intel chip knows that's slow, so he caches a bit. I think he caches 8 bytes. 8 bytes is a lot. It will run at the speed of a very old PCXT, and normally it will only run that long for a few seconds, of course, and then it will copy itself to RAM, the standard BIOS. But for me, at that point, it's simple, just copy the stream out. So I have one simple instruction: send blob of data, add a CRC, give some information about which blob it is. And it takes about 15 days to copy 4G. And I still got, let's say, this stack of PCs, so I don't want to deal with one UI. I didn't want to spend the next 5 months on copying those. So if you use the same algorithm and just copy it to RAM, at least the SPI is no longer the bottleneck. But then my serial link is slow. It's only 150 kilobit. So the process now is, okay, I've got this system, I have initialized it using serialize and QEMU, and I will dump 2 meg of memory, give it a day. And I'll do that from ROM. That will take about 10 minutes. So now I have a forensic copy of this first 2 megabytes. I'm so happy I've got RAM now. So I will copy this thing. And my first version of the stuff, running from ROM, is very limited. As you haven't got any RAM, you can only use registers, there's no stack, there's no heap. So it's very difficult to make a fancy program. So I had my program compiled twice, one with ROM-CC, left out almost all fancy stuff, and then again with GCC, with some relocation, and then I added a compression library. Sounded like a sensible thing to do. So a compression library sounded smart. So there's something called libzf. It's a very simple library. It's by its own telling, it is 50% on average binary, but on 0 pages I tested is 99%. And as end-use pages of a PC are cleared beforehand, so you don't infect memory from one process to the other process, there are a lot of pages that are empty. So that saves a lot. And the other thing is I started using my post dongle, and it's a very nice thing because it can actually cache a bit. So it has some memory, and the PC will send data using port 80, and the thing will cache a bit and send it as serial device to the PC. But it's not a real serial port, but I'm not sure how to call it. Anyway, you can't set a bit rate for this serial port. It just goes as fast as USB allows you to. And it runs about 400 kilobits per second, so that's a bit faster than the normal thing. And then it takes about 8 hours to make a copy, and that sounded reasonable, so that's the point where I stopped. If I wanted to make it faster, I would have probably need to make hardware like PCI Express cards, something like that. So that's not done. If you've got a motherboard with 4G of memory, actually it shows to the system as you've got memory above the 4G area. Because what you need, of course, it starts at the zeros, at the first byte, and then at some point in memory you actually need PCI configuration registers. And that's somewhere around 3.5G. So you have got about half of a G of memory that's overlapping with your PCI configuration space. So what normally happens that the Northbridge will allow you to split it up. So it gives you one bunch here, video RAM is masked, so that's not, and ROM is masked, and the part that's here is actually shifted. So you get a gap, and the rest is from 4G to 4.5G, or to 5G, or whatever the amount of memory you've got. But serialized as an application is a 32-bit application, so it can't access that one. And porting serialized to be a 64-bit application, that sounded like a bit over the top. So I used physical address extension as paging mode, and using 2 megabyte pages, I would be able to map a full G of data from the 4G to 5G physical address into a logical address space which is lower, and then use the same process and protocols again to dump them. So these are the two versions of serialized there are nowadays. I've got the standard version which does the simple stuff, read write bytes, long things, I/O, specific memory, and on the right side the stuff I added for myself, which is memory dump stuff, like a dump over serial, dump over post, which can be done from ROM because it's very simple. And when I add compression, I need to first copy it to RAM, so there's a RAM copy operation in there. And when once it's in RAM, it can do all those things and a bit more, like compress, give up a range, those kind of stuff. And then it's time for a short video. So I've got a lot of time to spare for questions, and then we can go to the demo for those who want. So first of all, before you can do forensic investigation on a machine, it first must be turned on and normally booted. So in this case I'm trying just to fill it with memory. This is the standard boot procedure. I'm booting Linux, and you will see the standard power on self-test codes showing up on the display of my dongle. And well, this is the standard view of the thing, and it takes a few seconds. Well, if people got a question down, maybe a good moment. A short one. Yeah. A good question. Perhaps because they are clearing the memory. And showing nice logos as well, yes. So this is the normal boot in Linux, nothing special here. This is my reference system. It's if people went to this tent, they would have seen it laying around once in a while with my bad soldering to show that I'm really a software guy, not an electronic guy. So it's booted now. You see this ugly wires. Because it's a reference system, I have the programmer already in place, so I do not need to remove it and for every iteration of testing have the memory removed. So this is the stock BIOS being removed. I need some place to store it. And here goes the serialized BIOS in it. Actually, the wiring is pretty resilient to short circuit. If you take scissors and scratch on top of them and short circuit the pin, nothing happens, which is good. So I replaced it, and I will showing a bit. Oh, it's still blinking. It's still doing normal stuff. So nothing happened yet. It's all boring. And on the left you will see the USB dongle, and I'm using that to reset the motherboard. I just heard you can use the HTX connector as well, but I did the other way. And you must be very good at counting, which I was not during the making of this video. So it's also, as I didn't have a good connector, you have to tweeze them in and make sure the dictators the right difference. And I've got pretty big hands, so it's slow. Oh, I miscounted, darn, yeah. To the left, to the right, which one should I pick? Is this right? Yeah, this is the correct one. Okay. So, they're in now. It's like professional stuff, right? You see the tape? It's like hacking. So I've got this small script, which is an I2C script. We're writing a command, and the system will immediately reboot and give me the serialized prompt. So this is the BIOS, which I programmed, giving the prompt of stuff. And when you enter, it gives you a new line. So you need to recompile QEMU and patch it a bit. The coreboot project gives you a good explanation how to do it. And then I will start QEMU, and I said, okay, there is a BIOS.bin here in the corner, and it will pick that up. So I'm booting without a hard drive. I don't need a hard drive. And set the BIOS in a local directory, and you need to use serialize, and it's on TTI S1, which has just got out of sight. So what you now see is all commands being sent over the serialized port to the motherboard and back are logged, which makes sense if you want to develop your BIOS yourself, because then you can pick out any difference between this initialization and your own initialization you did in your coreboot thing. And then you wait about 20 minutes, and then this goes on and on and on and on. Got some more coffee, please? Some more coffee? I need coffee. We wait some more. Yeah. And then we see this behavior. And then this is completely different. So we see read byte, write bytes. And what I did in the Lua script, I actually said if you are ever going to write to low memory, that's a big no-no. So actually, although it says it's going to write, it's blocked in the software. So I stopped QEMU. And now I'm writing some manual commands on using the standard serialized command. So I'm reading memory at byte 0, which is 53. I'm giving a long, giving a something long. I'm going to write it, so I'm writing a long value to show you its RAM. I will read it back, and then you would see it's actually having the same data again. So I'm very happy now. I said I'm going to dump some memory. And then actually the terminal emulator kicks in a bit and stops. So I'm going to use it without the terminal emulator using some script, and then you see the text coming in. So here's my memory dump. It's not all visible. That's not well. I should probably do something about that. So let's just put strings on top of it to at least make it readable. And apparently we're now in a block of zeros. Something like that. Oh, we're going to do it again. So now we see things you would normally see. You also saw a very short header which I add something like store and then an offset. And then I've got a very nice general changer with a lot of LEDs to be convinced data is flowing. Although you can't see it on the video, but that's too bad. So the next step is actually to start dumping using the post interface. I've copied the data to RAM by this time. You saw the prompt was a bit different. And what you can see here actually is the level, the number of data in the memory, or you should have seen. So this is the video again. So this concludes the presentation. And then I'll go back to the questions part.
Can we have an applause, please? I don't see a standard central microphone stand in this hall, so if you have a question, please come forward and I'll give you the microphone. Or the room is maybe small enough to just shout, I don't know. You have a question?
Is this tied to these any specific PC hardware like Southbridge initialisation and the Northbridge, or could this be used in any type of PC?
I would say use your imagination here. I designed it and developed it for a certain case, and in this case we had this hardware. I don't expect it to work out of the box on any hardware. You would need to do some work at least.
Right. So did you leave the hardware running all this time you were developing this?
Yes.
Right.
First, one of the simpler questions to procedure. How do you deal with cases like tripwires connected to fiber optic network cards? And to the more complex part, the IPME hardware is able to raise system management interrupts over the low pin count bus.
Yes, probably can, but those were not here at the time. So in a forensic investigation, you would typically be, let's say, very observative of those kind of stuff, and you may actually bump your head once in a while, doing it wrong. But well, we are lucky in this case, I guess.
Any other questions? Yes, I see you.
One possibility that you didn't rule out in the beginning of your talk, would it have been possible to just take the proprietary BIOS, disassemble it, and just put knobs at the place where it says wipe the RAM and boot on this?
Yes, that would have been possible, and actually I tried. But it's 2 megabyte I think actually of compressed BIOS code. So it's not like a very small program. So I took some effort to find the place, but you need to actually be able to decompress it as well and find out how it's linking together. And it's not the nicest code to read, as that part is not always meant to be run with RAM. So your standard IDA Pro will not recognize stack frames. It's partly Intel x68 real mode code, sometimes mixed with 32-bit code. So it's not the nicest environment, especially as you can't do, let's say, dynamic debugging as well. So you need to do full static analysis of mixed code, and it's a bit pain.
We have another question here.
So how much effort in personal weeks did you actually spend on this, and what crime would justify such a large effort?
Yeah, I spent a significant amount of time with it. In criminal investigations, my time is not the only time involved, so you must also think about we've got the time of the police, we've got the time of the judges and other stuff. So on the whole picture, the time spent by me would not have been the biggest cost in this kind of investigation.
That's great to hear. Can you at least shed a bit of light on the type of crime you are speaking here? In this specific case where you had this stack of servers, which is probably not murder, except someone threw them on someone else.
Well, then the short answer is no.
I can understand, I think.
We have another question here.
Yeah, I was just wondering. You have a hard disk with a reasonable sizey bit of RAM you're trying to dump. My first idea would be to just plug in a hard disk and write it there. Is there any reason why you didn't do that?
Yes, the reason is if you want to use the hard drive, you would need to have a much bigger understanding of the motherboard, initialize it much further, to be able to use the hard disk driver, or at least some part of the, I'm forgetting those names, but the ATA interface on the I/O side is not the simplest either, so you need to have initialize at least the ATA side and some more. So I choose the easy way out, having a lower transfer speed compared to having a better understanding of the motherboard, implementing a bigger and more complete BIOS. So that's the choice. In that sense, it's a cheaper investigation. Otherwise, I would have spent way more time.
Okay, fair enough. Thanks.
There are two questions at the other side. Unfortunately for you, he was first.
Hi. So I was wondering were you able to push some of the coreboot changes upstream, so talk to the developers and upload the patches and stuff like that?
I should have, I guess, and I think this presentation is a way to actually make known to the world that there are patches, but my patches are not that usable for the core boot project itself. It would be interesting for the forensic society, I guess.
Answer your question?
Yeah, I have a question. You mentioned already a little bit about talking to the vendor of the machines.
Yes.
Could you not ask the vendor, I think it's HP, if they can help you out and help you develop the tools that you use, because they would have better understanding of the motherboard layout and.
Yes, they would have, I guess. But the problem is, apparently people already got, let's say, magic visions about governments that they can manipulate all corporate companies around the world to do stuff for them. But in the end, we're just a customer. So you call them and say, okay, which machine is it? What is your subscription number? Do you have a licensing agreement? Well, would you please? Oh, well. So you know this process is not as easy as that. So you haven't got a contact within Bangalore, which is the manager over there of this specific motherboard. You would just start as a normal customer and then call a local authority and say, oh, okay, is your motherboard broken? We can send you a replacement.
We have, I see 3 more questions.
I'm sorry I missed the beginning of your talk. Could I ask you to browse through the slides one more time very quickly? And
I think we can do that privately afterwards,
okay,
if you really want.
Meanwhile, what changes did you do to so did you do changes to coreboot, or did you also do or did you only do changes to serialize for the hardware?
I did only do changes to serialize.
All right.
Not to coreboot itself. I did, of course, try to contact those guys and then see if it would be easy to implement the full BIOS, but they actually advised me against it.
So what chipset and CPU is on this machine?
Sorry?
What chipset and CPU is on this machine?
I don't recall by heart. I think it's an Intel ICS9 chipset.
Yeah, that's the Southbridge, Northbridge, and CPU is more important. Well, so anyway,
those are things that I need to. I forget.
All right. Yeah, that's fine. So I'm part of the coreboot team, and I'm happy to look at any patches that you.
Okay, well, you're welcome. If you want patches, it's cool. It's always nice when your work is being appreciated, so to say. Always nice when your work is appreciated.
So I'm curious why your serial speed is so slow. Is that because this specific card emulates only 16450 and not anything more modern, or did you try to run it in?
Well, it may be my mistake then.
Okay.
I guess. I didn't actually try to make it much faster than this.
Because most of them, I mean, since the early 90s can go way higher.
So how fast should it have gone?
I think 500 kilobit would be normal.
Okay. I'll try the next one.
So yeah, no, well, 115K to 100 is the maximum baud rate, but the serialized protocol is text over serial port.
No, at some point they started introducing higher frequencies. For example, if you have an ISDN terminal adapter connected over a serial line and it's also doing compression, then you get 128 plus a factor 2 for compression. So you need to feed it with 256 data, and I think most 16550As should be able to go at least 200 or 500 or whatnot. There's a couple of different models and they go way higher.
All good suggestions.
I want your patches to serialize for that.
I see 2 more questions there. The gentleman in the back was first.
Hi. So you briefly touched on the subject of the BMC, and if I remember correctly, the BMC has DMA, and also it is my impression that most BMC seems to be running on very old Linux system. Some of them you can directly access the configuration file through by just specifying the path in the web server, and a whole host of them have default accounts that you can't disable. If you wanted to dump the RAM, did you try that venue, or am I misremembering? Because I think the BMC has DMA.
I think you're right. It probably has. I expect the BMC to be connected using PCI Express partly and an LPC. So I think it's a, let's say, dual interfaced, and I expect to have the video on the PCI Express side. So probably also busmaster capabilities there. I did look at the content of the BIOS chip that belongs to the BMC. So I dumped it. I think actually I downloaded it. I think, and I had it in the decompiler. So I had it in IDA Pro. I didn't notice that it was Linux based, as far as I know. So I just touched on it, and I didn't make a full investigation. At that point in time, I felt like it was too hard to take that path.
We have only time for one more question. So I saw someone in the back there. Sorry you're too late, but you can come to the garrison afterwards, and you will get a private tuition.
2 comments. I used to work in embedded PCI development. Hot plug PCI is definitely possible, even with standard PCI connectors. You need to be a bit specific with how you develop the board, but it's possible. Sorry. And secondly, where you have a target system with empty DIMM slots, have you considered using those as connectors if you start with a blank DIMM board?
I have considered that, but I didn't dare to implement it.
Okay.
So those are ideas that are floating around. But then again, you take the path of the least resistance, and that you have, so it's not like there's one way that will solve it, and you take it new every time.
Yeah. One further comment: the reset pin on the ATX connector isn't called reset; it's called power good.
Okay, thank you. Can we have another applause for Ruud? Thank you.
So anyone wants to see the demo, which is a noisy one, and you've seen the video, so it doesn't add that much actually. You're all welcome at the Garrison Village, and it's if you are at T2 at the back side. So if you take the back row and walk out at the left, you would walk almost immediately into our tent.